Welcome dear students, we are on the CEC Gurukul lecture. We are in the series of electronic circuit and today we are discussing the thyristor, and thyristor is also known as the silicon controlled rectifier. So up to now we discuss the what is the thyristor and how it works. Now we see the characteristic or the mode of operation of the silicon controlled rectifier or the thyristor, and it works in the three modes, and this operation depending upon the biasing. First mode is the forward blocking mode, that is the off state. Forward blocking mode, first is the off state. Second is the forward conduction mode, that is the on state, and the third is the reverse blocking mode, that is the off state. It means the silicon control rectifier worked in the three mode. One is the forward blocking mode, second is the forward conduction mode, and third is the reverse blocking mode. We will discuss. There are the, you see on the screen that here we are having the 3 PN junction, that is J1, J2 and J3, and this is the SCR with the layer of the PN. This device has terminals. One is anode, you see, that is represented by A, second is the cathode, that is represented by the K, and third is the gate, that is G, and is attached to the P layer nearer to the cathode terminal. Now, an SCR can be considered as a two interconnected transistor, as we discussed in the previous lecture. So, it is seen that the single SCR is the combination of the one PNP transistor, that is represented by the Q1, and another is the NPN transistor. One is PNP and second is the NPN transistor, that is Q2. The emitter of the Q1 act as a anode terminal of the SCR, while the emitter of the Q2 it's act as a cathode. You see here, you see in the left hand side, you see in the Q1 anode is the Q1 emitter and the cathode is the Q2 transistor emitter. So now the third one is the gate, and the further the base of the Q1 is connected to the collector of the Q2. Base of the Q1 is connected to the collector of the Q2, and the collector of the Q1 is connected to the base of the Q2, and the gate terminal of the SCR is connected to the base of Q2. The gate terminal is on the base of the Q2, and in this manner we can get the thyristor. Now, the reverse blocking mode of the SCR. How we will work on the reverse blocking mode of the SCR? We discuss one by one. In the reverse blocking mode of the SCR, we see that the reverse biased SCR is reverse biased by connecting its anode terminal A to the negative and the cathode terminal K to the positive end of the battery. Here the cathode terminal with the positive terminal of the battery and the anode with the negative terminal of the battery attached here. See here. Now, this leads to the reverse biasing of the junction J1 and J3. You see here J1 and J3, which in turn provides the flow of current through the devices. In spite of the fact that the junction J2 remains in the forward biased condition, J1 and J3 are the reverse biased, while J2 is the forward biased. Now, in this state, the SCR behaves as a typical diode. In this reverse bias condition, only the reverse saturation current flows through the devices, as in the case of the reversed bias diodes, which is shown the characteristics curve we already seen here. Now, the device also exhibit the reverse breakdown phenomena beyond a reverse safe voltage limits, just like a diode. though that will work as a diode. But in case of the forward blocking mode of the SCR, we will see here the positive bias is applied to the SCR by connecting the anode terminal A to the positive and the cathode terminal to the negative terminal of the battery, as we have seen in the diagram. Under this condition, the J1 and J3 are the forward bias. Now, J2 is the reverse biased. J1 and J3 are the forward biased, but J2 is the reverse bias in this condition. Now, the current cannot pass through the thyristor except the tiny current flowing, a saturation current, as you see here in the diagram, and that is represented by the blue curve, which is a characteristics curve. That is the characteristics curve how it will work. This is a VI characteristics of the SCR. Right hand side we are having a forward characteristics, and left hand side of the graph and the lower side we have the reverse characteristics. In the forward characteristics, forward bias voltage we will get then when the gate turn on as the voltage V naught. After that it forward biased over the voltage, then we can get the holding current. After that the forward the on state we will get. Similarly here on the left hand side, then we are having the reverse breakdown voltage at VBR, then reverse characteristics we will get. Next is the forward conduction mode of the SCR, and this SCR can be made to conduct either by increasing the positive voltage applied at anode terminal A beyond the breakover voltage VB, or by applying the positive voltage at the gate terminal G, as you see here that the gate terminal, by increasing the positive voltage applied at the anode terminal A beyond the breakover voltage VB, or by applying positive voltage at the gate terminal G, you see here. Now, in the first case, the increase the applied bias causes the initially reversed bias junction J2 to break down at the point corresponding to the forward breakover voltage, that is VB. This result in the sudden increase in the current flowing through the SCR, as we have seen. Then the gate terminal of SCR remains unbiased. However, SCR can be turned on at a much smaller voltage level by proving the small positive voltage at the gate terminal. The reason behind this can be better understood by considering the transistor equivalent circuit of the SCR. Now, you see here in the diagram that these two are connected, Q1 and Q2 are connected, and here we can get the output. Here it is seen that applying a positive voltage at the gate terminal, transistor Q2 switches on state we can get, and it collector current flows into the base of the transistor Q1. Then this causes the Q1 to turn on, while the turn result in the flow of its collector current into the base of Q2. This causes either transistor to get saturated at a very high speed, and the action cannot be stopped even by removing the bias applied at the gate terminal, provided the current through the SCR is greater than that of the latching current. Here the latching current is defined as a minimum current required to maintain the SCR in the conducting state even after the gate pulse is removed. That is the latching current. When we remove the gate pulse, then it will having the minimum current required to maintain the SCR in the conducting state. So, in such cases SCR is said to be latched, and there will be no means to limit the current through the devices unless by using its external impedance in the circuit. This necessitates one to resort for different techniques like the natural commutation, force commutation, or the reverse bias turn off and gate turn off to switch off a conducting SCR. Basically, all these techniques aim at reducing the anode current below the holding current, and that holding current is defined as a minimum current to maintain the SCR in its conducting mode. So, this holding current keeps the SCR in the conducting mode. Similarly to the turn off techniques, there are also the different turn on techniques for the SCR, like triggering by DC gate signal, triggering by AC gate signal, and triggering by pulse gate signal, forward voltage triggering, gate triggering, DV by DT triggering, temperature triggering, and the light triggering. There are the many variation of the SCR devices, like reverse conducting thyristor, gate turn off thyristor, gate assisted turn thyristor. As per the requirement, we use these devices. There are others also, asymmetric thyristor, static induction thyristor, MOS control thyristors, light activated thyristors. Normally SCR have the high switching speed and can handle heavy current flow. So it makes thyristor ideal for many applications. How many applications we have? We have the lots of application in case of the thyristors, like we are used in the power circuits for the AC or for the DC. Now it is also have a zero voltage switching circuit. We will use over voltage protection circuits, use the thyristors. Controlled rectifier inverters also use the thyristors. AC power control use the thyristors, including light motors, etc. Pulse circuits we use it. Batteries changing regulator use the thyristor. Latching relays use thyristors. Computer logic gates, remote switching units, phase angle triggered controllers use thyristors. Timing circuits, where we use the thyristor, which is used in the on and off condition. IC triggering circuits, welding machine control use thyristors, temperature control system use thyristor. There are many devices which use the thyristor as per this requirement. Now, how many type of the thyristors? We define the some of the types of thyristor here. First, as we discussed, the silicon control rectifier. Second is the bidirectional control thyristor, that is BCT. And next is the gate turn off thyristor, MOS turn thyristor, that is MTO. MOS control thyristor, that is MCT. Light activated silicon control rectifier, that is LASCR. Static induction thyristor, that is SITH. TRIAC. Emitted turn off thyristor, ETO. Integrated gate commutated thyristor, that is IGCT. Gate assisted turn off thyristor, that is GATT. Comparison of the different thyristors. So we are having a various thyristors which can be used according to its application, and we will define one by one. Now you see on the screen there are the many types of the thyristor, and these are in the form of the many sizes and many shapes as per the requirement, but the principle is the same. You see the basic thyristors are shown here with the different outputs. Here we are having the different type of thyristor, and these are the symbols. By using this we can represent the thyristor. First is the silicon control thyristor, silicon control rectifier thyristor. That is also one of the most commonly used thyristor. They are having a high speed semiconductor switching devices. They are similar to the Shockley diode, and that but with an extra terminal. The chosen terminal for the construction for the SCR is the silicon, and SCR works like a silicon rectifier diode with an anode and the cathode, and it is having a gate. The anode is the positive terminal and the cathode is the negative terminal of the SCR. It has 4 layers of the alternating P and N type material, and it also has a has a additional control terminal which is called the gate. The presence of the gate allows the SCR to be triggered into the conduction. The gate required to trigger the SCR so that the conduction can take place, and it is a unidirection devices that allows the current to only flow when it is in the one direction and opposes the flow in the opposite direction. And on the screen, this is the SCR that is used in the most of the gadgets. The SCR can be switched on by either an exceeding the forward break over voltage or the gate current. The gate current controls the amount of the forward break over the voltage required switch the SCR on. The trigger that pulse through the gate terminal when the anode and cathode are forward biased applied. This switches the SCR into the conducting state. The current that flows between the anode and cathode, and once the SCR is in conducting, the triggered current will continue to flow even if the gate terminal is removed. When the anode and the cathode are in the reverse bias, the SCR will not conduct even if the trigger pulse is applied to the gate terminal. So it will be in the forward biased. Bidirectional control thyristor, that is the BCT. In this type of thyristor, we use the two SCR thyristor which are configured in an anti-parallel arrangement and forming a single devices, and it can be observed from a structure. It has the two separate gate terminals for each of the thyristors. As we are using the two thyristors, so we are having a two gates terminal. One gate terminal switches the current on in the forward direction, while the second gate terminal switches the current on in the opposite direction. You see here in the diagram, here the gate are, they are defining the two gates are. The two thyristor functions independently of the one another. Now, one major challenge faced in the construction of BCT was the crosstalk between the both the transistors. Therefore, a photo mask has been set up to prevent the effect of the harmful crosstalk when the BCT is under the operation. Next type of thyristor is the gate turn off thyristor, that is the GTO. In this type of thyristor, the turn on and off can be take place the main current with the help of the gate device circuit. So GTO comprises the two layers of the P type terminal to P type material and two layers of the N type material. So it is in the format of the PN, and they are also used in the high current and high speed switching applications, which include the chopper circuits and the inverters. In this type of the thyristors, the N plus layer at the cathode, you see here the N plus layer at the cathode and is heavily doped, and this increases the emitter efficiency, resulting in the low breakdown voltage at the junction 3. Now, to maintain the high emitter efficiency, the doping level at the P type gate is low. The junction between the P plus anode and the N base is also known as the anode junction. You see in the diagram here, this is the one type of the GTO junction, and here it is PN. Now, for the GTO, it remains on state. The P plus anode region must be heavily doped. This ensures a higher efficiency at the anode junction. It turns on when a positive voltage is applied at the gate terminal. It can also be turned off when a negative voltage is applied at the gate terminal. The device does not latch and requires at least 1% trigger voltage to remain in the conduction state. However, GTO has a heavily doped P anode region when it is in the turn off state, and then the turn off capabilities and the turn off capabilities are comprised for the thyristor to have a good turn off properties. The doping of the P plus gate region and the N plus layer between the anode needs to be heavily doped, then it will work in a better manner. Next is the MOS, turn off thyristor, that is also known as a MTO. In order to overcome the limitations of the GTO, Silicon Power Company developed the MOS turn off thyristor, or that is the MTO, by combining the GTO and a MOSFET. Now, MTO provides the same function as the GTO, but it needs only a signal level voltage to turn itself on and off state. So, also the structure of the MCT is almost similar to the GTOs. You see here the same diagram we have, it is the same turn off gate and turn off gate. Here we have the two gates, cathode, anode, turn on gate, and it is the turn off gate. Now, MOS control thyristor, that is MOS control thyristor, is the semiconductor device that combines the current and voltage of the thyristor with the MOS gate. MOS gate turn on and off. It is a high frequency and low conduction drop and high power devices, which is used for medium and high power applications. You see on the screen here, this is the MOS, gate, cathode and anode, and MOS is represented by this symbol. Now, the gate is not defining as an attachment. The structure has the three junctions, the anode, cathode and the gate. The P and PN layers are sandwiched between the anode and cathode. The thyristor is switched on when a negative trigger voltage is applied at the gate with regard to the anode. It would be switched off when a positive trigger voltage is applied at the gate with respect to the anode, and it is suitable for applications such as motor drivers, static VAR compensator, uninterrupted power supplies, etc. Now, the light activated silicon control rectifier, that is LASCR. LASCR is a type of SCR which is triggered using a light source. That's why name is light activated silicon. Then light source such as LED, and it consists of the three terminals like cathode, anode and gate. The trigger current is initiated through the light source. When the photon particles hit the junction of the junction, then it produces the electron hole pair, and this trigger current is supplied to the LASCR, which activated the gate terminal, and hence current flows through the devices. This also aids in the prevention of the electrical noise, disturbances and being generated. The power circuit and the light source circuit are electrically isolated by the LACR. The thyristor is made up of the silicon, and the glass lens in the LACR focuses the light from the light source on the semiconductor devices. So, the silicon pellet is situated at the bottom of the thyristor devices. The devices goes into a conduction state when light intensity dislodged the electrons in the semiconductor circuit. Now, you see here on the screen as a two arrows which represent the photon are falling on the thyristor. It is also having the anode, cathode and the gate. So, this is the thyristor. In the case of the static induction thyristor, the static induction thyristor is also known as the field control diode, and it is allows the conduction of the large current which have a low forward voltage and the turn off quickly, and it is a high frequency power semiconductor devices, and this device is on the off state if the anode is positive and gate voltage is 0. This makes the device behaves like a diode where the current is allowed to flow free from any obstacle. Now, you see on the screen, and this is the diagram of this type of thyristor. Now there are more we will discuss in the further lectures. Thank you very much.